Okay, we're on the bottom of page 8 in your physics manuals. We're going to review some trigonometry because you're going to use a lot of trigonometry in this class. And the first thing I want to just look at is basic right triangles, because basic right triangles simplify all the trigonometry. So we have, if we have a triangle here, it's a right triangle, which means it has one of the angles is 90 degrees. And we're going to analyze a certain angle. We'll say we're going to look at this angle here, and we'll call this angle, I don't know, theta. Okay. So we label all three of the other sides. So the side that's always opposite to the angle, whatever angle you choose, the opposite side we call the opposite. It's nice and easy. Okay, and the side that's next to it, and there's two of them that are next to this angle. There's two sides that are next to this angle. There's this side and there's this side, but this is the one that's not across from the right angle. So this one here we call the adjacent, which means next to, the adjacent side. And the one across from the right angle we call the hypotenuse, And so there's three different right angle trig functions that we can use. We can do, and so it depends on which sides of the triangle you have, on which trig function you're going to use. So we could take what we call the sine of the angle. The sine of the angle is the opposite side over the hypotenuse. We could use the cosine of the angle. That would be the adjacent side over the hypotenuse. The adjacent side over the hypotenuse. Or we could use the tangent of the angle, and that would be the opposite side over the adjacent side, and we don't use the hypotenuse at all on that one. And this is why in trig you probably learned about or wrote a story about Princess Sokotoa, which is S-O-H, sine is opposite over hypotenuse, C-A-H, cosine is adjacent over hypotenuse, and TOA, tangent is opposite over adjacent. Math teachers are weird, and they like to have you write a story about Princess Sokotoa. All right, so this is for a right angle trig, this right angle triangle. And you can use all these simplified versions of various trig functions. Another simplified version is what most of you call Pythagorean's theorem. This is not the full theorem. This is just a shortened Pythagorean's theorem that works for right triangles. If this side is A, and we'll call this side B, and the hypotenuse we'll call C, then another relationship is that A squared plus B squared equals C squared. Most of you call this Pythagorean's theorem, but there's actually a little bit more to it than that. We'll come back to that in a second. But this will work. You can use this as Pythagorean's theorem for triangles that just have a right angle. Okay, that's the easy trig. Next one, we're going to talk about the law of sines. The law of sines. This is actually pretty easy. This means you would use this if you do not have a right angle. So we have three angles here, and we'll say that none of them are right angles. We'll call this angle A, we'll call this angle B, and we'll call this angle C. And we usually use capital letters for the angles. The opposite sides, then we use as small lowercase letters. So this opposite side would be B, and this opposite side would be small a, and this opposite side would be small c. And the law of sine is simply that the ratio of the sine of an angle over its opposite side will always be the same number for any one you do. So I could take the sine of angle B and put it over little b, the opposite side, the length of the opposite side. There's going to be a certain number. That'll actually equal the same number if you do like the sine of angle C over its opposite side, or if you do the sine of angle A over its opposite side, they'll all be the same. So depending on what information you're given about a triangle, if you have sides and you have some angles, you can always use the law of sines to figure out what you're trying to determine. So that's kind of nice. And you might say, well, did this work? Does this work on a right triangle? Did this work on a right triangle? Yes, it does work. And you actually use it all the time. But sometimes I guess you don't think that you're using it. For instance, let's look at this angle here, theta, okay? And let's look at this angle here, okay? So this is 90 degrees. So let's just do the law of sines. Let's do it. So I could do sine of an angle. We'll do it sine of theta over its opposite side, which we're going to label as opposite, right? That should equal the sine of another angle. We'll use 90. We'll use this one here over its opposite side, which would be the hypotenuse. Okay, that's the law. That's using the law of sines. But if you look at this, okay, you might not have ever noticed this before. What is the sine of 90? If you put in your calculator, you'll see that the sine of 90 is actually 1. So if you look at that, then I could do the sine of the angle. I can multiply the opposite up to the top side, and the sine of the angle would be opposite over hypotenuse, which is right there. So you've used this all the time, and you probably didn't even realize that is the law of sines. That is the law of sines. It's just one of the angles that you used was 90 degrees, and the sine of 90 is 1. So this simplifies. See, this is the law of sines simplified whenever you have a right triangle. Okay, so we actually did use the law of sines there. Okay, I get one more thing about the law of sines. So I don't know if I can get you to understand this or not, but this is tricky because there are times when you're trying to use law of sines and it's not giving you the right answer. I'm going to try to draw a weird triangle here. I'm going to draw a triangle within a triangle. Okay, like this. And the first triangle we want to look at is this one here. Let's just look at this outer triangle right here. And here's an angle. Okay. And this triangle here, by the way, is isosceles. So we'll call this opposite, but we'll also call this opposite because they're actually the same lengths. Okay. Let's call this angle B. Yeah, that'll be good. Okay. So let's look at this triangle right here and try to figure out what angle B is. So what I might do, and so we'll call this side B, okay? So what I might do here is I would do sine of the angle over the opposite side, right? Sine of this angle. So right here, sine of this angle over the opposite side, which is this side of the triangle, okay? That would equal sine of B over B, okay? And let's say we know B, and we know this angle, and we know this opposite side, and you're going to try to do this. You're going to do all this math to figure out what big B is, okay? You could do that, and you would actually not have the right answer. And here's why. Let's look at the big triangle now, okay? Let's look at the big triangle, okay? And let's do the same thing. Let's try to figure out what this angle B is, okay? But actually, it'd be this angle here, right? So I could do, so we're looking at the big triangle now. Keep in mind, we're looking at the big triangle. Sine of this angle, sine of theta, over the opposite side, which would be clear out here, right? So it'd be out here. But notice, it's the same as this. It's the same as this, right? So sine of the big angle over opposite would equal sine of the angle we're trying to look at, which is right here, okay? I'll go ahead and call that theta. No, I won't. I'll call it C, angle C. Let's make it angle C. Okay, over the opposite side, which is over here still, it's B. Okay, and you'll notice that this, and this really are the same thing. Sine of theta over opposite, right? I have sine of theta over opposite, sine of theta over opposite, equals the sine of C over little b. This equals the sine of B over little b. And if you solve for B with this one, and you solve for C with this one, okay, which one is it going to be? Because this right here is an obtuse angle, and this is an acute angle. They're not the same angle. Okay, so which when I solve for the give me, and that's this weird thing here is called the ambiguous case. The ambiguous case, because which angle does it give you as the right answer? It always gives you the acute answer. So it would always give you the answer C. But see, that's the problem, because if you're doing a law of sines on this big triangle here, it won't give you this correct answer. It'll actually give you this one. So how do I get this answer? Well, it's actually pretty easy, because if this angle is angle C, this angle here is also the same angle. It's also angle C. So it's going to give you this angle. How do I get this one then? Well, these are supplementary. So all I have to do to get the correct angle is take 180 minus whatever answer it gives me, and that'll be the correct answer. So this won't happen very often, but what you need to realize is that if you're using the law of sines and you're trying to figure out an obtuse angle in the law of sines, it's not going to give you the right answer. So you got to know in your drawing if the angle you're figuring out is obtuse. If it's obtuse, then take 180 minus whatever you get for your answer, and that'll be the actual answer. It's always going to give you the acute angle, not the one you're looking for. I don't know if you understood that or not, but it's okay. So you probably won't run into it anyway, but I just thought that'd be nice for some people. Okay, the last thing we want to look at is called the law of cosines. The law of cosines. You'll be happy to know there is no ambiguous case for this. This will always work if you'd like to use it. So we use the law of sines and we use the law of cosines when we do not have a right angle. So we'll do it again here. Let's see. I'm going to make sure I label the same ones. A, B, and C. Okay, so this was angle A. This is angle B. This is angle C. So this is opposite side is, whoops, I messed that up. This opposite side here is C, and this is A, and this is B. And this is the law of cosines. So information I need is to have side, angle, side. I need to have two sides, and I need to have the angle in between them. And the law of cosines looks pretty familiar. C squared equals A squared plus B squared. This is what you call the Pythagorean's theorem. But that's not the Pythagorean's theorem. That's just a shortened version of Pythagorean's theorem, and you can only use that for right angles. So the law of cosines is fancy talk for Pythagorean's real theorem, which is C squared equals A squared plus B squared minus, there's an extra part, minus 2 times A times B times the cosine of the angle between both of those legs. Okay? So in this case, if I have A and B, here's A and here's B, so the angle in the middle of them, it would be C. So it'd be the cosine of C that I'd have in the middle there. Okay, so I can use this, and this will always work to be able to figure out, whatever I need. Maybe I need side C. I can figure out this opposite side if I know these two sides and the angle between them. I can use the law of cosines. And you might say, well, would this work for a right triangle? And yes, it does. So let's say we're trying to figure out what C is over here, and here's A and here's B, and the angle in between A and B is 90 degrees. So what happens to this equation if this angle C or angle theta right in here is 90 degrees? Well, put cosine of 90 in the calculator. What do you get? You get 0. So this whole term goes away. And you get this. And then for the rest of your life, you call this Pythagorean's theorem. Nope, it's not. Pythagorean's theorem is actually C squared equals A squared plus B squared minus 2AB cosine of angle C. I guess I should make it angle C. It's just with right triangles, just like the law of sines collapse down to something you're familiar with. The law of cosines, or Pythagorean's theorem, collapses down to another Pythagorean's theorem that you're more familiar with, because the angle here in the middle is 90 and the cosine of 90 is 0. So this thing disappears. Okay, so that was a review of trigonometry. We're going to use that a lot. Hopefully you understood all that.